Hi guys, this lesson is on 4.4, the universal wave equation. So in Physics 20, waves will move in a straight line at constant velocities. This means that we can use good old V equals d over t to describe the motion of a wave since we're doing constant velocity. So what does this mean in terms of the wave terminology? So displacement and time. Well, if we talk about the displacement of a wave, so how much distance one wave covers, that would be the term wavelength from the last lesson. Wavelength is denoted as the Greek letter lambda. The time of a wave, since we skipped lesson 4.1, we're going to have to go back a bit and talk about what the time of a wave is. So the time of a wave is 1 over f, and we don't know what f is yet. So f is called the frequency. What frequency is defined as is how many oscillations per second. So you can do this in a number of contexts. If I think about my lesson from 4.1, I talk about how many times can a Canadian goose flap their wings per second? How many waves can travel per second? That kind of thing. So the units for this are hertz, or what hertz actually are seconds to the -1. And just to jump back to Math 10C, what does that exponent law mean? Seconds to the -1 is like 1 over second. How many oscillations per second? That's really what the fraction bar means. So if we put all this together, there's a little blurb here explaining that displacement is the wavelength, like we talked about, and it's measured in meters. And the period, or the time it takes for one wave, is going to be 1 over the frequency. So if we put that into this formula, we've got wavelength being displacement and 1 over frequency being time. If I do a little fraction work, division of a fraction is the same as multiplication of the reciprocal. I get lambda times f. And that's exactly what this universal wave equation says. So this is just a manipulation of V equals d over t from Science 10. So here's the units for everything. Velocity is still meters per second, wavelength is meters, and then probably the easiest way to think about frequency is 1 over seconds, but we do call that hertz when we're talking about waves, so you need to know both. Okay, a few examples here. We have a sound wave, or the speed of sound in 0 degrees Celsius air being 331 meters per second. The speed of the same sound increases in air that's 20 degrees to 343 meters per second. If the frequency of the sound is 2.50 times 10 to the 3 hertz, what is the difference in wavelength? So the first thing I kind of zoom in on is that word difference. So in math, what do we mean by difference? We mean we need to subtract. So ultimately, we're doing this question for 0 degrees Celsius, for 20 degrees Celsius, and we're subtracting our answer. So what you can gather from this question, and if you did the reading assigned for the last lesson, is that the speed of sound depends on the temperature of air. It can travel faster through warmer air. So let's write down our universal wave equation. Let's sub in what we know, or rather let's manipulate first, because what we're trying to find is the wavelength. So I'm going to manipulate first because it's a very simple equation. Wavelength is going to be the speed of sound divided by the frequency. For 0 degrees Celsius, they told us 331 meters per second. And the frequency isn't changing here. How many sound waves per second are going through this air is not changing. It's remaining constant. Okay, so we're going to use this number for both calculations. Doesn't matter if you sub in the units hertz or seconds to the -1. They're both the same for frequency. And here we go. My wavelength, and you could put 0 degrees Celsius in the subscript if you wanted to keep it straight. I'm getting 0.1324. So I'm just going to write 3 sig digs here, 132. And its wavelength, which is measured in meters. Now let me go over and do 20 degrees Celsius. So no need to manipulate the formula again. I've already done that work. I can sub in my speed at 343 meters per second. I can do my same frequency. It hasn't changed. And I'm getting for 20 degrees Celsius, my wavelength, or lambda, to be 0.1372, but I'm going to write it to 3 sig digs. Now I have to actually answer the question. The question said, what is the difference in wavelengths at these two temperatures? So I need to take the big one and minus the smaller one. And remember, even though I'm writing 3 sig digs down for these numbers, I'm using all of the numbers that were calculated, right? I'm not rounding off until the very end. So I'm getting 0.0048, which is fine. You can say that. You could say 4.80. Actually, I'd have to add a 0 after there to get my sig digs. Or 4.80 times 10 to the -3 meters. Or, since we work in metric in Canada, you can easily convert this to something that might be more easily worked with. Like on your unit exam for this unit, I probably would have put the answer to this question in millimeters, because this is a much simpler answer. So remember, we can always convert to what makes the most sense. So at 20 degrees warmer, the difference in wavelength of the same frequency wave traveling, sound wave traveling through air, is going to be 4.8 millimeters different. Okay, you're floating in a tube on a lake. I really hope we get to do this summer. And you notice that you bob up and down 4 times every 5 minutes. You estimate that the distance between the crests is 4 meters. What is the estimated speed of the waves in the water there? So, what we have to figure out is we're not told the frequency right off the bat. Remember, frequency is oscillations per second. We are told 4 oscillations every 5 minutes. What is this? We can say this is bobs, for bobbing up and down, I guess, per 5 minutes. But remember, we want this to be per second. So how many seconds are in 5 minutes? 300 seconds. I won't do sig digs here just so we can learn the concept, but yes, I should write that as 3.0 times 10 to the 2. Now, I want to make this how many bobs per 1 second. So if I set up something like this, what would we have done back in junior high math? If you're thinking cross, multiply, and divide, you're correct. So 4 bobs times 1 second divided by 300 seconds, I'm getting my frequency to be 0.013 hertz. So you would do 0.013 bobs every second. So you wouldn't even bob up and down once per second. And that makes sense. You're sitting on a tube in the lake. You're not going up and down very fast. If you were, you probably would be getting seasick. Now we have frequency, and the distance between the crests, which is a fancy way of saying wavelength, that's the length of one wave, is 4.0 meters, and we want to figure out the speed. So there you go. I've listed my variables. I look at my formula sheet and I see the formula. The universal wave equation looks like this. I'm subbing in my numbers now. And I'm getting the speed of the wave going through the water to be pretty slow, which I would assume is happening. 5.3 times 10 to the negative 2 meters per second. So that's all there is to the universal wave equation. It's really just a simplified V equals D over T using wave terminology. So the hardest part can be just reading the question and figuring out. They might not tell you the word wavelength like they did in this question. They might say something that means the same thing, like the distance between the crests, the distance between the troughs, something that's equivalent to wavelength. So it's really reading comprehension because the formula is so painfully easy. You've got questions 5 to 9 on page 410 to practice this equation. And I'll meet you back here in a week for the very last Physics 20 lesson called the Doppler effect. Let me know if you need any help.